Okay, our last speaker is Markus from New York University. He's going to talk about Tachis, higher order submarine logic with credits for expected costs.
All right, great. Thank you for that introduction. So yes, I'm Markus, and I'm going to be telling you about Tachis, which is our program logic for expected cost bounds on higher order probabilistic programs. This is a joint work between all of the people up here, and my collaborator Simon is also at Splash. Okay, so as we've seen a couple times now, one thing we care about when analyzing probabilistic programs is their expected runtime. So let's focus on an example here. I've got this program coin toss, which is going to repeatedly flip a coin and terminate the first time that it lands on heads. So I've augmented this program with this special tick1 instruction, which, as was again described before, is a no-op, but allows us to ask the question, how many times do we expect this tick1 function to be called? Okay, so this is not a trick question, and this analysis is pretty standard. We can let t be a random variable, describing how many times we've executed tick. And then we can basically just look at the program by inspection here and cook up a recurrence relation for the expected value of t. Okay, and so again, in this case, this is not a very tricky recurrence relation. You can see that the expected number of calls to tick here is 2. All right, so a natural question here, which hopefully I'm leading you to, is, well, how can we verify these kind of recurrence relations in cases where you can't just inspect the program and see that they hold? So some recurrence relations may depend on more complicated functional correctness properties, and we want to verify those as well. Okay, so one approach which has been fairly fruitful in the deterministic setting is this work on time credits. This was initially pioneered by someone named Bob Aguirre. And the whole conceit here is that you equip an existing separation logic with this special time credit resource, $x. So the approach here says that the logic will require, every time the program takes a step, that the prover give up 1 time credit. And so overall, this means that if you can close a proof of a specification that has a total budget of X time credits, you also know that you have a runtime bound of X steps in the execution of your program. Okay, so in the deterministic world, this is a pretty nice way to structure these kind of logics. It gives you a lot of really expressive local reasoning principles. So the fact that runtime upper bounds compose additively means that they have a very close relation to separating conjunction of resources, which is good for giving credits to different parts of your proof. It also means that time credits give you the frame rule applies to time credits, and so you can specify, for example, that tick1 takes 1 time credit. And you don't need to worry about any other time credits that might be kind of floating around the ambient state of your program. The frame rule allows you to basically ignore everything else that could be happening and just focus on the cost of the statement you're currently executing. Okay, so Aguirre pushes this work pretty far in his initial paper, deriving some rules for amortized reasoning from these time credit rules. And there's also a wealth of research going down this road for the deterministic case. I've listed 2 of them here, but there really are many more. Okay, so then going back to our initial question, can we use these time credits to prove expected cost bounds in a randomized setting? Okay, so let's try it. Here's the coin toss example we've already kind of verified on paper so far. And I'll just unroll the computation tree to give us a little bit more to look at. So what we would want to say is that a budget of 2 credits is enough to execute this program in some sense. And let's just try to verify this with the regular time credit rules. Okay, so first we have to execute tick1, and this costs 1 credit. And then the program is going to flip a coin and branch on the result. Okay, and the rules for time credits say that because we have 1 credit before the branch, we need to verify both branches with a budget of 1 time credit. And now things are kind of starting to go off the rails here. When we flip true, we have 1 time credit, but we don't actually need it because the program terminates immediately. And in the other case, when we flip false, we don't have enough credits to verify the recursive case here. Okay, and so you can see that no matter how many credits we start with, we are eventually going to exhaust them all with a sufficiently bad execution. Okay, so what's the fundamental issue here? At its core, the problem is that time credits give you a good way to reason about the upper bound of the maximum cost across all program traces. But in a probabilistic setting, each statement also has a likelihood that it's executed. And so this impacts the expected cost of executing that statement. Okay, so what we want to do is regain the ability to reason about these likelihoods in a way that doesn't lose us the great local reasoning features that you get from cost credits. Okay, so how do we fix this? Well, in Tachis, we have a new formulation of cost credits, which lets you prove a rule like the one I've listed here. This rule says that you're allowed to double the credit that you have in the case where you sample false at the expense of losing all the credit in the case that you sample true. And so intuitively, this is OK because we have a budget of 1 credit, and the expected budget here is still 1. It's fair coined. OK, so let's apply this rule. You see that now in the branch where we immediately terminate, we have 0 credits, and that's fine. And in the branch where we don't terminate, we have 2 credits again, which is enough to verify this recursive call. So we can recursively apply this procedure on and on and on, and we get this closed proof that says 2 time credits is enough to verify the coin toss program. OK, so with this example under our belts, here's a summary of our contributions. So in our logic, we use this new version of cost credits that can prove these kind of expectation-preserving cost rules. That's our jargon for it. We also have an adequacy theorem, which is in many ways very similar to the ones presented in these other logics, including the one by Aguirre, which instead of giving you an upper bound on the total cost of your program, gives you an upper bound on the expected cost. Tachis also lets you define your own cost model, so your own definition for what it means to cost, or what the cost is of taking any step. And this is nice because the languages we support also have a wide variety of features. So in particular, we support higher order, stateful, recursive programs. And this is a generalization of the deterministic work that you might see in logics like the Iris $. And of course, all of this too is formalized in Iris. OK, so before I go on to some examples, I want to briefly show you the full version of the expected cost rule. So I've written it up top here. But just I'll walk through it informally. So let's say we're trying to verify a cost budget of X for a program that's about to take a random step. So it sort of clearly suffices to show that for every outcome of the random step, in this case 0, 1, or 2, it's enough to verify each case with an expected or with a cost budget of X minus whatever the cost of taking that step was. So this is like the worst case reasoning that you've seen in other more classic logics in the deterministic case. But of course, our cost credits also give you a bit more flexibility. So if you're trying to prove an expected cost bound of X, we say that the prover can verify any bound for the 3 outcomes. And as long as the expected bound is within their initial budget X, regardless of whether or not the branches increase or decrease, you still can close this proof and say that the expected cost is bounded by X. OK, so I just want to emphasize the fact that this is a local reasoning principle. If you have X cost credits kind of in your hand, and you're taking a random step, you're able to condition the value of your cost credit. And you don't need to worry about what your other credits might be doing. They could be stuck in some invariant somewhere or be in some proposition you don't care about. You really only need to care about the invariance that you have in your proof state right in front of you. All right. So for the rest of the talk, I'm going to go through 3 different examples of things that we can verify in Tachis. Here's the one which I think by law you have to include in a presentation about expected costs. So here's quicksort. So you'll notice that our implementation of quicksort is higher order. It takes in a comparison function as an argument. And so our specification for quicksort is also higher order. It takes in a specification which says our comparison function has an expected cost of m. So what we want to do is we want to verify that we have some overall expected bound on the quicksort program, which hopefully is going to be n log n, as you'd expect. And so the way that you would do this on paper is you would write down a recurrence relation which looks something like this, where you have some linear term associated to the cost of doing the partition function, and you've got 2 recursive terms where the argument depends on the sizes of the left and right sublists after you partition the list. Okay, so of course, our program is not directly picking the sizes of left and right sublists. Our program picks a random element. And so the challenge in verifying quicksort is getting a correspondence between picking an index and the the recurrence relation here, which is written in terms of the rank of that index. Okay, so how do we verify this in Tachis? Sort of unsurprisingly, we're going to use that expected cost rule, like I've mentioned a couple times before. So given any unordered input list L, it's not too tricky to define a function which relates the index we sample to the sizes of the left and right sublists. And it's also not too tricky to prove that if you're picking this index at random, this function here is going to be mean preserving, so we can use it in our expected cost rule. But concretely, this says that if we start with t of n credits, using our rule, we will have enough credits for both recursive calls, and we can close this proof and verify this expected cost bound. So I just want to note that this is a non-trivial problem because it relies on the correctness of partition with respect to the comparison function. And also the fact that nowhere in this process did we have to compute any closed form for this recurrence relation. Really, this separates the concerns of verifying your program meets a recurrence relation and proving asymptotic bound or something like that. We did mechanize this as well, but that was just for fun. Okay, so totally changing gears here. Let's say that for some reason we want to sample a bunch of coin flips and we only have access to random byte sampling. So for example, you might be getting your random bytes from dev random or something like that. You can sample coin flips in sort of a naive way by taking a random byte and just reading the last bit. And this works, but it's very inefficient. And so one thing that you might ask is, can you do better, right? And can you prove that you can do better? Okay, so in Tachis, I mentioned this idea of cost models before. One thing that we can do is we can define an entropy cost model. We can say that we're going to prove specifications where the time credits are used to make random samples here. And so sampling a random byte is going to cost 8 bits of entropy. So in Tachis, we can say for this section, that will mean it costs 8 credits. And so this naive approach here samples has a cost of 8 bits for every coin flip. And so, so we want to do better than this program here. Okay, so one way to do this is instead of wasting your entire byte when you sample a coin flip, you're going to cache the value of that byte in memory, and you're going to use it for multiple calls to this function. So here the program batch flip allocates a memory cell, which can store our random byte, and it allocates a counter as well. And batch flip returns a function where every time we call it, it's going to kind of pick off the next bit that we've sampled so far and return it as the result of our coin flip. So of course, after we do this 8 times, we're going to run out of these cached bits. And when we call batch flip again, it's going to need to refresh the byte stored in memory, and then it can continue onwards as you'd expect. Okay, so can we prove that this program is more entropy efficient? We can. So in our cost model that we have before, we can prove this specification for batch flip. It says that if you have 8 bits of entropy, or if you have a cost of 8 bits of entropy to set up the initial state in memory, batch flip will return 3 things, really. It returns a function, an invariant, and a specification for that function. The invariant keeps track of some amount of cost credits and also the current state of memory. And the specification says that it only costs 1 credit in order to sample a coin flip and update this invariant. Okay, so in particular, every 8 calls, this invariant will accumulate enough credits in order to do that refresh in memory. And so this is an example where we're able to derive these kind of amortized reasoning principles from the rules for credits inside Tachis. I'll also just note that this is a pretty clear example here where we're using a higher order stateful specification and higher order functions and all of the adjectives you see in front of Iris papers. Okay, final example, because I think I am running out of time. I want to show you this program k-way merge. So let's say you have k lists and you want to merge them together into one big, or k sorted lists, sorry, and you want to merge them together into one big list. Okay, so one common way to do this is you make a min heap out of the smallest element in every list, and iteratively you pop elements from the min heap, pull them back in from the list you took it from, and so on and so on. Eventually, you get a sorted list. Okay, so what's the runtime of this program? Well, if we're able to insert and remove from our min heap in O of log k time, and there are n total elements, then we do this n times, we get a total bound of O of n log k. Okay, so half of you might be thinking, where's the randomness in this program? This is totally deterministic. maybe you're in the wrong session. And the other half are probably thinking, can you really get these bounds without failing an undergraduate algorithms exam? So you can. There's an implementation, a randomized implementation of heaps called meldable heap, which does get O of n log k inserts and removes in expectation. And that means that when we do this deterministic looking proof in Tachis, the randomness reasoning can be totally encapsulated. Okay, and this is sort of just a nice feature of working with these time credits, which can also support the kind of reasoning that you would do in more typical cost-aware logics, like the one I talked about with ATKI. So we do this in our paper. We provide a cost-aware specification for an abstract heap. We prove that meldable heaps meet this specification, and also we prove the k-way merge against this abstract notion of a cost-aware heap. Okay, so I think that's all I wanted to talk about, but thank you for your attention, and I'm super happy to take any questions.
I have a quick question.
Sure.
So have you done any evaluation with your logic?
So we've done quite a few examples, which we've listed in our paper. But unlike some of the talks we saw before, like we're not automated. This is all by hand. So
I
yeah.
see. Do you think it's possible to have something like a similar execution engine for the logic?
I mean, maybe. We've thought about automating parts of the logic, but I mean, we're sort of targeting expressivity in these sort of logics. I mean, it's coming up with these expectation preserving functions is a difficult problem, and it would be hard to automate, I think. Yeah.
Thank you.
But on the other hand, for algorithms which have a pen and paper analysis, I think that a lot of times they have like recurrence relations, which can be translated into these, something we can verify. So different approach.
Thank you very much. So let's thank the speaker again. So this is the end of the session.